All right, welcome to the last topic, reviewing limits. As you probably have noticed, this week is just a lot of review. We're going to use the piecewise function that's graphed here below to find the different things that are being requested in the table below. So let's start with, just jump right in here. So I want to find the limit as x approaches -1. Now, I'm also looking at the fact that this says -1 with a little negative sign after it. That means -1 from the left. So if you remember back with my kids, what I always suggested was pretend like you can't see anything beyond where x is -1. So maybe you take a piece of paper and you cover up the entire graph, except for everything to the left of -1. So you have something that looks like this. Now, what I'm going to be able to do then is move this all around. But if I cover up everything to the left of -1, what I'm asking myself is, can I make a prediction about where my output will be when I reach -1? So looking at my graph and I follow along, it looks to me like, and our graph is counting by ones on the y and ones on the y-axis, and it looks like halves on the x-axis. So if I'm making a guesstimate about what I will get as an output here, that looks like it's going to be y = 1. So that's what I'm going to write here, is that we'll have an output of 1. Now, if I want to figure out what my limit is as we approach x from the right this time, or sorry, as we approach -1 from the right this time, well, now I just move this so that it's covering up everything that's not to the right of -1. And once again, I follow along my graph and I ask myself, can I make a prediction about what my output will be when I reach x = -1? And to me, that looks like it's going to end up at y = -1. So that would be my guess, is that it's -1. Remember, a limit is a educated guess. And then, sorry, I forgot to change that one. That should be -1 again right here. So as x approaches -1 from both the left and the right. Now, this is when we said, okay, look at what's happening right around -1. And you have to say that you can make the same prediction from the right side and from the left side in order to have this limit actually exist. And we have two different limits that we've written here. One is 1, one is -1. Because these don't match, what we say is that, remember that old line that you guys love from Mean Girls, that the limit does not exist. Okay? And then finally, the last column in all of these is asking for the output at -1. So if I plug in -1 to my function, what do I get as an output? And if I look at my graph, there is no output because there's no closed circle anywhere along x = -1. So this is undefined. Okay, let's do one more together and then I'll have you try the other two on your own. So let's go to 2 this time. Okay, so now we're going to say, let's start with 2 from the left. So I'm looking at my graph and I'm asking myself, can I make a prediction about what my y will be when I reach x = 2? And it looks like I can make a pretty good prediction here of 2. So looks like when x = 2, or when x reaches 2, y will be 2. Now I come from the other side. Okay, now I'm looking at from the right-hand side, and I ask myself, as I'm following along this graph, and I come closer and closer and closer to x = 2, what does it look like my output's going to be? Well, this time 1, 2, 3. It looks like my output is going to be -4. All right, and then I look at it as an overall limit, and I say, because these two things don't match, this limit, once again, does not exist. In order for us to be able to write something down in this third column, the previous two values had to be the same. So if these were both 2, this would be 2. Okay? And then f of 2. So if I look at when I plug 2 into my function, what is my output? Now, we look for any closed circles, and I probably should move that white square there. We look for any closed circles along the line x = 2, and you should only ever have 1 if it's a true function. And right here I do. I have my output is -4, exactly. So my output is -4, which just so happens to match one of my limits. So I'm going to have you go go ahead and try the next 2 rows. However, I want to make one small change on your picture. I would like this right here to become an open circle. So if you can just make that an open circle right there, it's a little more interesting when we start filling in the table. Okay, go ahead and pause the video, come back, and when you're done, check your answers. All right, so hopefully this is what you have. The interesting thing about that last one is that your limits actually do exist from both, from both the left and the right, but your overall value for that function is undefined right there. Okay, let's keep going. All right, so now we're going to look at the other ways that we found limits. First of all, we can find a limit by doing what we call a direct substitution. And a direct substitution just means take that value that you're using to find your limit at and plug it right in. So if we try that here, we're going to get, if I plug in 2 into my expression, I get something sort of interesting happen. I end up with 4 minus 4 over 4 minus 2 minus 2, which is 0 over 0. And we said we can't determine what the limit is based on this information. So we have to try another approach. So that's your answer for this first little section here. We can't use direct substitution right now. You might be able to in the future, but we can't at the moment. Okay, pause the video for a minute, go on to Desmos, use Desmos to graph this function, and then come back and we'll continue on. So when you graph this on Desmos, you're going to get a graph, and it might not show you this open circle right here, but it is going to be an open circle there. It's a hole in the graph, and we know that just from our previous experience with rational functions. If you were to factor this, you would see that x minus 2 is a repeated factor. So there is actually a hole in the graph, which is why we can't use a direct substitution here. So we have our function graphed. Now, we can look at this and we can estimate our limit. So from this, remember, we look at as we move along this graph and we get closer and closer and closer to x equals 2 from both the left and the right hand side of our graph, we start to notice that it looks like we're going to get an output that's somewhere between 1 and 1.5. Okay? Remember, our graph here is counting by halves. So we know it's somewhere between 1 and 1.5. So you could estimate, maybe it's 1.25, maybe it's 1 1/3, maybe it's, you figure out what your estimate is. I'm going to say, maybe it's somewhere between 1.25 and 1.33. Okay, that's a good estimate, somewhere in there. So it's kind of an imperfect science when we use our graph to estimate. However, we can then try using a table on our calculator or again in Desmos. So remember, in our table, we get values that are really close to 2, but just a little bit bigger and a little bit smaller on either side of 2. So our process was always that we used values that looked like this for x, and then we used our calculator to actually find out what we get when we plug those values into our function. Now you can use Desmos for this too. It's really nice on Desmos because you can create a table right there and just plug in the values you want for x. So go ahead and take a minute and figure out what those values are and come back and we'll talk about them. Okay, so using your calculator to find those values or using Desmos to find those values, what you should see is that as we get closer and closer and closer to 2 for x, we can start to see this value for y approaching something. And what would your guess be that you would get when you arrive at 2? And using our table, you might guesstimate that it's going to be 1.3333 repeating, which we know is 1 1/3. Okay, now the last thing we want to do is talk about how we can find out what the limit is precisely. And that's when we did this using an algebraic approach. And to do so, we had to factor the original value or the original function. So we're looking at the limit as x approaches 2 of x squared minus 4 over x squared minus x minus 2. And what we said is we should be able to factor that, right? So we can factor the numerator as a difference of squares. We can factor the denominator. And then we see there's a giant 1 right here. Okay, so we get this limit as x approaches 2 of x plus 2 over x plus 1. Now there's no danger at this point of doing a direct substitution, so I'm going to go ahead and plug in 2 for each of my x's and see what I get. So my limit ends up being 2 plus 2 over 2 plus 1, which is 4/3, which is the same as what I had up here. Okay, just as a refresher, go ahead and try this one from start to finish. You're going to graph, estimate your limit from the graph, watch out for any potential holes. You're going to use your table to estimate the limit from the table, and then finally factor it and look for giant ones, and then try to do a direct substitution there. So pause the video. This might take a couple minutes. Come back and check your work. So let's highlight the important pieces here. From the graph, there will be a hole again because there will be a repeated factor in your rational expression. But estimating from your graph, it looks like your limit will be 3. Okay, that's a good estimate. From your table, you probably had values that look like what you see on the screen. And that's an easy one to make a pretty educated guess here to get 3. And then algebraically, again, we factor it, see that giant 1. Once we've gotten rid of the giant 1, now we can go ahead and substitute in x equals 1 into our expression to get 3. So 3 different ways to get 3 as a value. All right, good work. One more video.